Hello students, today let us continue our session from hydrocarbon chapter, from which we are going to see about the physical and chemical properties of alkanes and their conformations. Let us see first of all the physical properties of alkanes. Physical properties of alkanes are depending on the molecular mass of the compound. When molecular mass increases, the physical properties also be altered depending on it. So generally physical properties are dealing about the state of the matter, color of the matter, then the smell as well as melting point, boiling point, solubility, density, refractive index, dipole moment, etc. So in this, these alkanes are in general, they are colorless and they have no odor. Okay. And their density is very smaller than water. So alkanes that can float on the surface of water. And the next one, the physical state of alkanes, they are generally existing in all the three states, say gaseous state, liquid state and solid state. So the alkanes that contains least number of carbon from 1 to 4, they can exist in gaseous state. And the compound having 5 to 17 carbon atoms can able to exist in liquid state, and that of the compounds having greater than 18 carbon, they are in solid state. And these solids are waxy solid and very soft also. The difference in electronegativity of carbon and hydrogen is very less. They have weak interactions among them. Also, they possess a weak van der Waals forces. And when you discuss about melting point and boiling point, the boiling point, melting point, both of them increases with the increase in their molar masses. The next one, solubility. I said the compounds are non-polar. Alkanes are non-polar. Non-polar substances used to dissolve in non-polar solvents. So, these alkanes do not soluble in water, but they are soluble in organic solvents like ether, carbon tetrachloride or chloroform, benzene, etc. Let us discuss about the boiling point of some isomeric alkanes. Let us take an example of butane and pentane. Both of them are successive members of alkane and they do differ in their molar mass of 14 units. As I said, the molar mass increases, boiling point also increases. You just compare the boiling point of N-butane and N-pentane. N-butane, it has only 273 Kelvin, but N-pentane, it has 309 Kelvin. And let us find the boiling point of their isomeric alkane. N-butane, it has 273 Kelvin and its isomer is isobutane, whose boiling point is 261 Kelvin. Similarly, for N-pentane, it is 300 Kelvin and isopentane 301 Kelvin and its neopentane, it has 282.5 Kelvin. So, why the boiling point decreases when for the isomeric structures of alkane? First reason, they are approaching the spherical shape. See, here the butane and the pentane are in a linear chain. And when it goes to its isomer, it takes one branch. So, the length of the chain reduces. Further, it goes to the another isomeric. Still, the length of the chain decreases. As the length of the chain decreases, the molecule, it approaches to its spherical shape. So, first point, you can say due to the approach of spherical nature. And its surface area decreases. When it approaches that sphere form, its surface area decreases, or you can say the area of contact decreases. So, area of contact decreases and hence van der Waals forces also decreases. So, van der Waals forces decreases. So, the van der Waals forces is a common force which is present in all the covalent compounds. So due to approaching of spherical state and its area of contact decreases, as well as van der Waals forces also decreases. These are the reason for the decrease in boiling point of isomeric alkanes. After the physical properties of alkanes, let us find the chemical properties of alkane. The chemical properties of the alkanes are just discussed on combustion, substitution, controlled oxidation, isomerization, aromatization, reaction with the steam and pyrolysis. So let us see the first reaction, combustion. What do you mean by combustion? Combustion is burning of a compound in oxygen. So where excess of oxygen is to be taken. Let us take methane, the first member of alkane. When it is burnt in oxygen, it is completely converted into carbon dioxide and water. And during this, it liberates the energy of about 390 kilojoule per mole. At the same time, if I take butane, butane is C4H10. This is also on complete combustion in oxygen. It gives carbon dioxide and water, for which the enthalpy change is found to be about greater than 2800 kilojoule per mole. So you can balance the equation. The first one, it has only one carbon, CO2, 4 hydrogen. So 2H2O, oxygen is 2 times, totally 4 oxygen. In the next case, it has 4 carbon, so I can write it as 4 CO2 and 10 hydrogen. So the water becomes 5 2s are 10. 4 2s are 8, 8 plus 5, 13 oxygen. So I should multiply this oxygen by 13. But 13 oxygen atoms only I have in the product side. But here it makes 13 into 2, 26. So to get 13 oxygen, the number is divided by its atomicity 2. So when you divide 13 2s are 26, 26 by 2 equal to 13. So you are getting 4 2s are 8, 8 plus 5, 13 oxygen. So this is the reason, upon heating of just 1 mole of hydrocarbon, they are able to release about this much highest enthalpy. This is because they are used as fuels. Now let us take the general reaction for the alkane. What is the general formula for alkane? That is CnH2n plus 2. This is burnt in oxygen, where it gives n times of carbon. So I will get n times of carbon dioxide. And I have 2n plus 2 time of hydrogen. So I will get the other one is water. Here I should take n plus 1 time of water. Why is it n plus 1? See, hydrogen I have 2n plus 2. So you can multiply the hydrogen, it is in twice. Up 2 into n, 2n you got. 2 into 1, 2 you got. So n plus 1 of water, that satisfies the number of hydrogen of general formula alkane. Now let us solve number of oxygen. In product side, I have n times of O2 in carbon dioxide and n plus 1 time of oxygen in water. So let us take, this is 2n times plus this is n times plus this is 1 time of total oxygen is present in product side. So let us add 2n plus 1, n equal to 3n plus 1. This is what 3n plus 1 of oxygen atoms. What I said? We are taking that molecular form. So when we find the atoms of oxygen, then the molecular form of oxygen to be divided by its total number of oxygen. So the total number of oxygen 3n plus 1 is divided by atomicity of oxygen. So this is the general representation of combustion reaction of alkane. Okay, here we have taken the oxygen in excess, I said. Suppose the oxygen is insufficient for the combustion of alkane, what we will get? C4H10. Let us take butane. In presence of insufficient of oxygen, that means I didn't take excess, that means the amount of oxygen required for butane I didn't take, where I will get carbon and water. So the carbon is deposited as carbon black. So this carbon black is the useful residue from which we are able to manufacture ink, printer ink, as well as it is used in filter, RO filter and all we have, in which the carbon black is dumped in it. So these are the useful purposes of carbon black. This is obtained when hydrocarbon is burnt in insufficient amount of oxygen. So I have 4 carbon, so carbon 4 times, 10 hydrogen, so 10 times of 5 times of water, 5 oxygen I have, so I can take this is 5/2 of oxygen. And one more thing, in this combustion reaction, the amount of energy calculated is just for 1 mole. That's why we didn't alter the number of moles of the hydrocarbon. Instead, we are just adjusting the number of oxygen atom, because these are the calculated enthalpy of the compound. If you are satisfying with the number of molecular oxygen, the amount of energy should also be altered. This is the reason these combustion reactions calculating for 1 mole of the compound. That's why we are taking 1 mole of alkane with the required number of oxygen. Next, let us see the substitution reactions of alkane. That alkane, it contains 2n plus 2 number of hydrogen. All those hydrogen atoms are replaceable hydrogen atom that can be replaced by a suitable group. In this case, I have taken methane. Methane, it has 4 hydrogen atoms. All these 4 hydrogen atoms can be substituted by chlorine. But the reaction is possible only upon heating. The heating that requires the temperature of 573 to 773 Kelvin. The high amount of temperature that can be given by using the ultraviolet light or sunlight, or you can take that heating sources only. You can represent the heat in the form of UV or as H nu. H nu is also one of the energy, that is the light energy obtained, that is UV. Instead we can make use of H nu also. So both of them, it represents the energy required for the reaction. So first time, let us take the chlorine. This chlorine, first of all, it replaces one of the hydrogen. I have 2 chlorine atom. So one chlorine atom replaces the hydrogen, other chlorine atom that combines with the replaced hydrogen, and it is left as minus HCl. So I am getting CH3Cl. This is chloromethane, or it is methyl chloride, common name. It has still 3 hydrogen atom. So another molecule of chlorine I am taking. So that chlorine also you can write Cl. One of the Cl with the hydrogen, there is minus HCl. Where the hydrogen is replaced, that got filled with chlorine. So you are finding dichloromethane, or it is methylene chloride. Then further I am taking with 1 more mole of chlorine. The 3rd hydrogen atom is being substituted. So I am getting trichloromethane, or it is called chloroform. And the 4th hydrogen atom of chloroform is once again replaced by chlorine. So I am getting tetrachloromethane, or it is carbon tetrachloride. Okay, this reaction, we take that sunlight or the high source of energy. What is the purpose of taking this? See that this is used to break the chlorine atom homolytically. So when the covalent bond is homolytically broken, we will get the free radicals, the most reactive species. So substitution reactions in alkanes, that follows free radical mechanism. So the free radical means, these are highly reactive, and the reaction once it commences cannot be stopped. and it still continues until the completion of the reaction proceeds. This is what the type of reaction that takes place in ozone layer, where the freons that liberates that free radical chlorine atom that continuously depletes, that means decreases the concentration of ozone, where ozone is converted into oxygen. So we can't be able to terminate the reaction once it gets commenced. So the reaction, actually the free radical reaction, it starts with 3 steps. The free radical reaction, usually it initiates with the homolytic cleavage of halogen, and then it gets propagated. After that only we have to terminate. So let us see initiation step. In initiation, the chlorine that undergoes homolytic cleavage in presence of sunlight. Homolytic cleavage, both the chlorine atom that share their shared pair of electron to each. So I am getting Cl dot with Cl dot. So I have got 2 chlorine free radicals. And this chlorine free radical, once it is formed, immediately that substitutes the methane. So the second step, it starts with the propagation. So let us have the 4 hydrogen atom of methane with chlorine free radical. Once again, one of the carbon hydrogen bond undergoes homolytic cleavage. So let us write C H H H H with chlorine free radical. Let us consider this carbon hydrogen. Here it takes that homolytic cleavage. So this hydrogen with the free radical takes this chlorine, it is converted into HCl. So now I am having methyl free radical. It is methyl free radical. This methyl free radical, it adds with one more molecule of chlorine, where once again the chlorine undergoes homolytic cleavage. So I am having CH3Cl and Cl dot. See that chlorine free radical once again initiated. This chlorine free radical that approaches that chloromethane, it forms methylene chloride free radical and HCl. So it continues. So we can write CH3Cl plus dot, it gives CH2Cl dot plus HCl. So one of the chlorine only, the hydrogen, each step you have to reduce the hydrogen. So the hydrogen with the chlorine, that goes HCl. And the next step will be CH2Cl, that is methylene chloride free radical that combines with another chlorine atom. So I am getting CH2Cl2 plus Cl dot. And this chlorine free radical interacts with methylene chloride. So I will take the other one of CH2 Cl2 plus Cl dot, it gives CHCl dot, CHCl2 dot plus HCl. Then this CHCl2 dot with another chlorine molecule, it follows homolytic cleavage, and I will take CHCl3 plus Cl dot. Still it continues because it has one more hydrogen atom that can also be removed as CCl3 free radical with the HCl. So let us write CHCl3 plus Cl dot, it gives CCl3 free radical plus HCl. Then the CCl3 free radical adds with the molecule of chlorine, it gives CCl4 plus Cl dot. So these are the steps involved in propagation. So the propagation actually initiates the chlorine free radical at the end of the every steps. So I have to stop the reaction. How I can stop? That I should give it in termination. The termination takes place either by terminating the 2 chlorine free radical combined to give chlorine molecule, or one hydrogen free radical can combine with the chlorine free radical to form CH3Cl, or 2 methyl free radical they can combine to form ethane. See that the termination step that involves termination, either chlorine free radical terminates with another chlorine free radical to give chlorine molecule, or the chlorine free radical that can terminates reacts with the hydrogen free radical to form HCl, or the methyl free radical that terminates with another methyl free radical to form ethane. So there are three steps. This is the first step, initiation. This is the second step, propagation, and this is the third step, termination. So this is what we are discussing about free radical substitution. So free radical substitution, it involves homolytic cleavage. Alkanes, they do undergo substitution reactions with halogen. It is called halogenation reaction. But alkanes do not undergo nitration or sulfonation. This is because the least stability of alkyl intermediates. Next chemical property of alkane is controlled oxidation. Usually alkanes do not undergo oxidation reactions, but under the high temperature and pressure and in presence of a suitable catalyst, they may undergo oxidation to yield useful products. Let us take an example of methane. Methane on oxidation, upon heating with the copper metal at 523 Kelvin and under 100 atmospheric pressure. This gives methanol, CH3OH. So methane on oxidation in presence of catalyst copper at 523 Kelvin and 100 atmospheric pressure, it gives methanol. You can balance 1 carbon, 4 hydrogen, the oxygen is twice the time, so multiply this is by 2, this is also by 2. Next, if same methane, it reacts in presence of molybdenum oxide on heating, where it is converted into formaldehyde and water. Formaldehyde, or you can say methanol. It is an aldehyde. This is methanol. Find the suffix. This is alcohol, OL. This is aldehyde, AL. And you can balance the reaction. 4 hydrogen, you have 2 hydrogen, 2 oxygen, you are finding 2 oxygen. So the equation gets balanced. The next, I have ethane. This is an oxidation with manganese acetate, CH3COO twice Mn. It gives rise to ethanoic acid, CH3COOH plus water. So to balance the reaction, this side I have 3 oxygen, so I should multiply this is by 3 by 2, because 3 oxygen atoms alone there. And to make it as a molecular form, that means I am multiplying the whole equation by 2. So where you are taking 2 times of ethane, it gives 2 times of ethanoic acid. 3 plus 3 6, 6 2s are 12, I have 3 plus 1 4, 4 2s are 8. So I should take 2 more water over here. Oxygen, 2 2s are 4, 4 plus 2 6. So this 2 will be cancelled when it is multiplied by 2. So this is what controlled oxidation. And here I have taken the primary alkanes, methane and ethane. If I have the tertiary butane, CH3 thrice CH, this is an oxidation by KMnO4. It gives its corresponding alcohol CH3 thrice OH. That means it forms tertiary butanol, butyl alcohol. But this reaction cannot undergo by primary or secondary alkane. Only the tertiary alkane it gives tertiary butyl alcohol when it is oxidized by potassium permanganate. The next reaction of alkane is isomerization. So isomerization, it is nothing but when a straight chain compound is taken in presence of anhydrous aluminium chloride and hydrogen chloride, it gives rise to its isomeric form. So a linear chain structure that gives rise to a branched one is called isomerization. So let us take N-hexane. N-hexane, it contains 6 carbon atom. So I am taking CH3, CH2, 4, CH3. 4, 4, 5, 6. So this is N-hexane. When it is treated with anhydrous aluminium chloride and HCl, This is undergoing isomerization to form 2-methyl pentane and 3-methyl pentane plus CH3, CH2, CH, CH3, CH2, CH3. These two are considered as a major products. But during isomerization, we will get some minor products also. But minor products never be considered in chemical reaction. So, we are taking only the major products of this reaction. The next one, aromatization. Aromatization, that means conversion of an aliphatic hydrocarbon into aromatic hydrocarbon. So, aromatic hydrocarbon that has minimum of 6 carbon atom in its 6-membered ring. So, you have to take either N-hexane or the substituted hexane or the carbon having more than 6 atoms that may undergo aromatization. For the aromatization, it requires the metallic oxides like chromic oxide or vanadium oxide or molybdenum oxide. At the temperature of 773 Kelvin, it gives benzene. So, in aromatization. So, let us take CH3, CH2, CH3, CH2, 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 CH3. This is N-hexane. In presence of vanadium pentoxide or chromic oxide or molybdenum oxide, and at the temperature of 773 Kelvin under 10 to 20 atmospheric pressure, this N-hexane undergoes dehydrogenation. So, it is converted into a 6-membered ring of benzene. So, benzene it has C6H6. But in N-hexane, what is the number of carbon? 6 carbon atom. But hydrogen is 14 hydrogen. So, rest of the hydrogen is left as 4H2. So, 8 plus 6, 14. So, this is known as aromatization. If you want to prepare toluene, what is toluene? Toluene is a methyl substituted benzene. This is what? Toluene. Then, what kind of compound you have to take? Nothing. You have to take the methyl substituted hexane. See, in this you have 6 carbon in a ring and the substituent has 1 carbon. Totally there are 7 carbon atoms. So here if you have a substituted ring, that means the second position of methane, that is CH2 group, when it has methyl substituent, you will get it. So let us write the equation for the substituted benzene. So preparation. So CH3, CH, CH3, CH2, 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 CH3. So this is 2-methyl hexane. When it is heated with vanadium pentoxide or chromic oxide or molybdenum oxide at 773 Kelvin under 10 to 20 atmospheric pressure, we will get toluene. Plus number of hydrogen will be the same. 4H2 will be removed because in this you may find 7 carbon. So 7 2s are 14, 14 plus 2, 16. So here you are finding 5 plus 3, 8, 8 plus 8, 16. The next reaction is reaction with steam. Steam is the vapor at its very high temperature, the water vapor at its very high temperature. So let us take methane with steam in presence of nickel. See the temperature at 1273 Kelvin. Methane decomposes water into carbon monoxide and hydrogen. The mixture of carbon monoxide and hydrogen is known as water gas, and this water gas is a very good synthetic reagent. From this water gas we can synthesize most of the chemical compound. That means the organic compound can be synthesized from water gas. So to balance the reaction, I have 4 plus 2, 6 hydrogen. So this is 3H2. This is what? Reaction with steam. The next one, pyrolysis. What is called pyrolysis? Pyrolysis is nothing but only heating the compound at a very high temperature but in the absence of air or oxygen. So the higher number of alkane during pyrolysis, it split up into its fragments. That means the alkanes or alkenes having lesser number of carbon than its reactant. For example, let us take N-hexane. When it is heated to 773 Kelvin, it may undergo dehydrogenation. That means a molecule of hydrogen is released where I am getting hexene, the position of double bond somewhere else. So I can write even hex 1ene. Or it may give rise to butane and ethane. So this is butane and this is ethane. Or it may give rise to propane, ethane or methane. So, and methane. So these are the products which have lesser number of carbon than its reactant. Similarly, dodecane is the constituent of kerosene oil. From the kerosene only the dodecane is taken. When it is heated at the temperature of 973 Kelvin in presence of either nickel or platinum or palladium, it gives N-heptane and pentene. Along with that, it forms other products also. That's all the chemical properties of alkanes over. Now let us find conformations. Already we have discussed about conformations in one of the video. But in this case, we are going to discuss about in little bit detailed manner. So the conformations that may give rise to the two different representation of alkanes. Usually alkanes have sp3 hybridized carbon. They have a three-dimensional geometry of tetrahedral. The tetrahedral, we said it is a multiplanar structure. The molecule that can even be represented, the tetrahedral form of alkane can even be represented in the form of Sahas and Newman projection formula. See, let us take that Sahas projection. In Sahas projection, I have taken an example of ethane, C2H6. And the two carbon atom that is linked, this is carbon-carbon bond. It has 3 hydrogen atom on both of the carbon. The straight line, that is the chemical bond between the carbon-carbon, let me write in a tilted way. Instead of writing horizontally or vertically, I am just writing in an inclined way. So it is little bit tilted. So this is one sp3, this is one sp3 hybridized carbon. Both of them, they have the 3 hydrogen atom. I am designating the hydrogen atoms of both of the carbon as A, B, C, A, B, C. So this molecule, if I rotate, because conformations and its isomers are possible due to the rotation of carbon-carbon single bond. That means it is treated as a free rotation. So the conformation as a result of free rotation about carbon-carbon single bond, it may give rise to different rotamers or conformers. So the stability of rotamers and conformers, the conformers which might be an eclipsed form, staggered form or a skew form. But at the same time, the rotation about carbon-carbon single bond is not that much free. Anyhow, it requires some amount of energy. That energy is found to be about 1 to 20 kilojoule per mole. Why very less amount of energy is required? Because the adjacent chemical bond, they experience a weak repulsive forces. So due to the weak repulsive forces between adjacent bond, the rotation, during the rotation of carbon-carbon single bond, that experiences a strain in the rotation. That such strain due to carbon-carbon single bond rotation is called torsional strain. And the stability of conformer is the staggered form is more stable than the skew form, which is then eclipsed form. I will explain how later on. And what is called dihedral or torsional angle? The magnitude of energy required, that is the torsional strain, is depending upon the angle of rotation between the adjacent bond, that is called dihedral angle or torsional angle. So let us discuss about how that carbon-carbon single bond undergoes free rotation. See, let us take an example of C2H6. So both of the carbon, it has 3 hydrogen atom and both the carbon atoms are sp3 hybridized, and the 3 carbon atoms just I designated as ABC. You see the first structure in which the carbon with the HA and the carbon with the second carbon with the HA is exactly one behind the other. So when you view the molecule from this carbon atom, you can't able to see the rear carbon atom. So the rear carbon that has HA is exactly just behind the front carbon HA1. So we unable to see the HA of rear carbon. Now I rotate that bond. So during the rotation, the position of the rear carbon, the position of hydrogen of rear carbon gets altered. See, the HB it comes over here, HA, HC here it comes. So this is here exactly they are just behind one another. Such form of Saha's projection is said to be eclipsed form. After the rotation of the carbon-carbon single bond, the rear carbon that changes its relative position with respect to the first carbon into different manner. This one is said to be staggered form. The staggered form is more stable because it experiences less repulsive forces among the hydrogen atoms of both of the carbon atom. But in this eclipsed form, the hydrogen and hydrogen, the adjacent bonds are very near to each other and they experience a strong repulsive force. So when repulsive force is maximum, stability will be less. So eclipsed form is less stable than the staggered form of Saha's representation. And the same ethane molecule can be taken in Newman projection formula. This is Newman projection. Here both of the carbon atom is considered as a ring. So one carbon atom that is in the front ring, the other carbon atom exactly to the behind the ring. So when two rings are closing each other, you may find only the front ring and not the reverse, the back side of the ring. So the ring form of carbon, both the carbon is represented in a circular one. And you may find this is what the origin of the circle, and from the origin I have given a lengthier bond, and I have given 3 more bonds over the circumference of the circle, that is given as shorter bond. That means the circumference which has shorter bond is said to be the carbon at the back side of front carbon. So the origin with the lengthier bond is said to be a front carbon. So when you keep both the carbon one behind the other, HA, HB, HC which have longer bond is with front carbon, and the shorter hydrogen, that is means the shorter bond with the 3 hydrogen is belonging to the rear carbon. And this molecule which can be rotated to an angle of 60 degree. So when I rotate the first one, the position of rear carbon it gets altered. See that the HA, HB, HC and all just turned into 60 degree rotation. Once again I am taking that 60 degree rotation where HA goes to the HB carbon, HB goes to HC and HC goes to HA. Once again after the 60 degree you may find the HA, HB, HC are exactly opposite to each other. After the 2 more rotation of 60 degree, you are getting the molecule just like that of the first one. So I can represent this is 1, this is 2, this is 3, this is 4, this is 5, this is 6 and this is 7. So the structure 1 and 7 are identical, where both the front and rear carbon, they have their same hydrogen which are just behind one another. But every 60 degree rotation of that ethane molecule, it gives rise to the different spatial arrangement of hydrogen atom that belong to rear carbon. And you may find the fourth structure of the one, in which exactly the rear and front carbon, they have their hydrogen in opposite manner. Such form is said to be staggered form. And the structure 1 and 7, which are identical and they have their own hydrogen just one behind the other, such forms are said to be eclipsed form. And the structure 2, 3, 5, 6 are called skew form. So, upon the rotation of carbon-carbon single bond and depends on the degree of rotation, it may give rise to the different rotomers or the conformers. They are said to be eclipsed form, staggered form and skew form. Eclipsed form, the repulsive forces will be greater because they are very close to each other. Staggered form, the hydrogen atoms of both front and rear carbon far away from each other. So this staggered form experiences very least forces. And in this skew and gas form, skew form where you are having the hydrogen closer to the other one, gas form where the hydrogen far, but the hydrogen atoms of them are not with the same designation. Those are said to be skew and gas, but let us consider it is skew only. So we can write the stability of these conformers is eclipsed, smaller than skew, which is smaller than staggered. So this is what the stability of these conformers. And I told the energy barrier, whether it undergoes the free rotation? No. Due to the angular strain, it may experience some hindrance during the rotation. The hindrance of rotation, it requires that amount of energy to overcome the forces of hindrance, that is given by about 1 to 20 kilojoule. So, energy barrier from one form to another form is 1 to 20 kilojoule per mole. This energy barrier, why it come across? This is due to the weak repulsive forces between adjacent bonds, that is called torsional strain. Because it doesn't undergo free rotation, it requires some amount of minimum energy because of repulsive forces. Such forces that cause that energy barrier is called torsional strain. And dihedral and torsional angle, this is depending on the angle of rotation, the energy barrier can be reduced, or we can say it may even taken to 0. See that in staggered form, it has the least energy barrier. So, in this case, the angle of rotation is about 180 degree. So, when it goes the maximum angle of rotation, then the angular strain that can be minimized. Such difference of that angle is said to be dihedral angle or torsional angle. And in the Saha's projection, the groups which are attached to carbon and hydrogen is present at an angle of 120 degree. So, this is what the conformation for ethane molecule. Ethane molecule, both the carbon atom they get, only the hydrogen atom. If I take butane, we can easily explain the other thing. An example to explain this concept, N-butane. So, N-butane formula CH3, CH2, CH3. So, about these two carbon only we are going to rotate. So, front carbon, rear carbon, both of them they have two hydrogen and one methyl group. that can be represented in Newman projection formula. See the first one. Both the carbon atom, they have their groups very close to each other. That means they are exactly just one behind the other. So the distance between these two groups attached with the carbon-carbon single bond, as the distance is very minimum, they have maximum repulsion. So the maximum repulsion is observed in the structure of 1 and 7. This is both of them are similar. Upon it completes a one complete rotation. So such the compounds have least stability and maximum energy. See, it is given in the energy diagram, potential energy diagram. So the fully eclipsed form, it is at its highest energy of about 20 kilojoule. It can have maximum energy. And from fully eclipsed to I am going here, it takes about 60-degree rotation. So the rear carbon, the groups of rear carbon, that it takes its other position. And once again I am doing that next rotation where the CH3 with another hydrogen HH, that and all just altered. So this is fully eclipsed, and when it goes to the next rotation, you may find the front and rear carbon groups are exactly opposite to each other. So in this, the distance between the groups far from one another, so it experiences least repulsion and hence they are more stable, and energy associated with the staggered form is very less. So it is approaching the zero energy level. So the eclipsed form, it has very high energy due to maximum repulsion, minimum distance. But the in between of eclipsed and the staggered, I have 4 more structure. Those are said to be gas form. In this gas form, the repulsion is in between of eclipsed and staggered. So the energy possessed by this gas form is also just in between of eclipsed and staggered. See, the gas form, it has lesser energy than fully eclipsed, but more energy than fully staggered. So gas form is in between of their stability. So the stability of this can be written. The staggered is more stable, which is than gas, which is than eclipsed. Okay students, that's all. Let us close our today's session up to the conformations of alkanes. We will see in our next class with alkenes and their reactions, properties, etc. and all. Until then, bye bye.